In this section, we are going to look at an interesting formula called Kramer's rule. But before I get there, let's write down a few things that I'll need. So we'll start with A, let it be a square matrix. Size n by n, I suppose. And consider A to be made up of its columns. Define A subscript I of B. This is a function. Define it to be the same as matrix A, but with column I replaced with the vector B, which is in Rn. So in particular, what we'll have then is AIB will be the same matrix, except in column I, we put a B. Now we're ready for Kramer's rule. Let A be an invertible n by n matrix. For any vector B in Rn, the unique solution to AX equals B is, and we'll give it the formula for each xi. This is the determinant of that matrix AIB divided by the determinant of matrix A. And this is for all of the i's. So for this proof, once again, we will let A be listed according to its columns. Now we already know that the identity matrix looks like the following: E1 up to En, like so. Then we also know that if I do A times I sub I of X, let me go ahead and write this out in longhand. I'll leave that there for a minute. But remember now, this right here means that I'm going to replace column I in the identity matrix with an X. So you'll still have E1, and you'll still have up to EI minus 1, except now you'll put an X in the I column. And now we can go ahead and multiply the A through to each and every one of these vectors. Now take a look. Let me get a handle on these AEs for a minute and see what we get then. If I look at AE1, that's the same as A times this vector, a 1 with a bunch of zeros after it. If you remember, all this does is pick off column 1. So if I do AE2, that's going to simply pick off the second column, because that E2 has a 1 in the second place, just like the E1 had a 1 in the first place. And you can keep going from here until you get all the way up to AEN, and that will be AN. The only one that needs a little bit more work is AX, and for the time being, we're not doing anything with it. So let me continue my equation. I have A times I sub I of X. I'm going to take off from here. So we see that that is the A1 vector until I get to A sub I minus 1 vector. And then I have AX. And then I have AI plus 1 until I get to A sub n. But now we are saying that AX is equal to B, so let me go ahead okay, and that of course equals A sub I of B. So thus A times I sub I of X equals A sub I of B. Take the determinant of each side. On the left, I can break the determinant up as so. Then I can divide by the determinant of A since it's not 0. And finally, let's get a handle then on what I sub I of X is. So if we look at it, to get its determinant won't be that bad. I just want to write it out a little bit. This is E1 up to EI minus 1. And then we've replaced the ith column with an X. And let me write it out in longhand. I don't know how many rows I'll need. I'll just kind of write some and see what happens. There's the first one, and then we have this one. And as we go on, dot, 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 let me get to column I. When we get to column I, then I'll have an X1, X2, dot, 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 up to an Xn. So there is the vector X. And let's end it at that. Let's compute the determinant of I sub I of X by expanding along row I. So what does row I look like? Row I, let me just write it in here, starts with this. It has a 0, then a 0, dot, dot, dot. Then we have a 0. And then in row I, we have xi. That's the only possibly non-zero item in there. So when you do it, where is it at? Well, that x happens to be in position II. So let's go ahead and calculate then what I sub I x's determinant looks like. So when we look at the first 0 in the list, that's row I, the first 0 on the list occurs in row I, so we will have -1 to the 1 plus I times 0 times, and then we would have had the determinant of I sub I1. Remember, that's where we delete row I and column 1. And then we move on, -1 to the 1, well, to the 2 plus I times 0 times I sub, here we're going to stay in row I, but we moved on to the second column. And this, of course, continues, plus dot, 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 plus, let me get to I. So we have -1 to the I plus I times x sub I times I sub II plus dot, 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 plus -1 to the I plus n times 0 times I sub in. Well, of course, everything is 0. All that we have left is -1 to the 2I times xi times I sub II. All right, well, let's see what we have here. Well, -1 to the 2I is going to be 1, positive 1. Then we have xi, and then we have this determinant. Let's see what happens when you remove a row and column, or the I row and the I column from this. Let's just look small for a minute and see if we can get a handle on what this looks like. So here is a very small one. Let's strike out this and then this. And then what do we have left over? What is left here? It looks like when I reassemble, I'm going to have this. So it's an n-1 by n-1 identity matrix. So let me write that in as a step 2, so later on when you look at it, you can follow it. So this is the determinant of I sub n-1, which is still 1, but I think it's important to know what it comes from. So I have 1 times xi times 1, which is x sub I. So come back up here. Well, where was I at before? Let me have you. There she is. Let me copy this guy. All right, since we have this, I can now go ahead and replace the determinant of I sub I with x sub I. So pretty ingenious way of getting this thing to work out. And for small matrices at least, doing these by hand is very nice. Let's do an example. So we'll use Kramer's rule to solve. Here we have -5x1 plus 2x2 equals 9. And then we have 3x1 minus x sub 2 equals -4. So to solve this then, what I do is for my x1, I go and in the numerator, I guess, I will put the answer column, which is 9, -4, but then I'll put the rest of the matrix A. Let me put A equals -5, 3, 2, -1. So what we do is we replace the column of the variable we're looking for with the answer column, and then we of course take the determinant of A itself. All right, well, let's go ahead and write these out then. So for this, I do my normal cross whatever you call this thing. 9 times -1 will be -9 plus 8. And the matrix itself, its determinant is 5 minus 6, so that's -1. So this ends up being 1. Very nice. And then x sub 2 equals, this time what I'm going to do is leave the first column of A alone, but now I will replace the second column with 9, -4, the answers. And I already have the determinant of A. So let's go ahead and do this. I have 20 minus 27 all over -1, which is 7. So my x equals 1, 7. So for 2 by 2 is a pretty good formula. Here's a problem that we could have done this before this section, although I guess I figure it's not too bad to illustrate the power of determinants for some of these things. So determine the values of t for which the system has a solution. And here it is t times x1 minus 2x2, and that's equal to 1. And then we have 4t x1 minus 4t x2, and that equals 2. Now we know that this thing has a solution if the matrix of coefficients is invertible. The solution to this is surprisingly Kramer's rule free. The solution, or there will be a solution, if and only if the matrix of coefficients is not equal to 0, as I said. And I really don't see a need, unless they want you to try to figure out what the solutions to the system are, which I might do that. But let's take a look at the determinant that we have here. Then we get -4t squared plus 8t, and that's not supposed to equal 0. Let me take out a -4t out, and that will leave me with t minus 2 inside of the parentheses. That's not equal to 0. So from this we can see that t should not equal 0 or 2. So that completely answers the question that was asked there. Now if I actually wanted the solutions, all we have to do then is let's take the determinant of this matrix, and as we said, we had -4t squared plus 8t. And now let's find solutions then. So if I want x1, I'll take and replace my matrix, or at least the column of x1s, with 1, 2, and leave the second column alone. But don't forget to divide by these things. All right, so in the numerator then, we get -4t plus 4 all over -4t squared plus 8t. I guess I could take out a 4, even a -4 if I wanted to. Let me have a -4t minus 1. From the denominator, I'll factor out a -4t and that leaves me with t minus 2. I can really only take out the negative 4's, so we get t minus 1 over t times t minus 2. So I guess that's a solution. You kind of see that there's no question that you would not be allowed to have t equals 0 or t equals 2. And then x2, if you were so inclined. This time I'll leave column 1 of the original matrix alone and replace the second column with my answers. And I'll divide by negative 4t times t minus 2. Let's see what we get up at the top. 2t minus 4t all over negative 4t times t minus 2. All right, and in the numerator, let me factor, well, I can actually just write negative 2t like so. Cancel out, well, that's nice, I can take out a t. So I can take out a negative 2, and it looks like what I'm going to be left with is 1 over 2 times t minus 2. If A is an invertible, n by n matrix, then we know it has an inverse, and in fact A times A inverse will equal the n by n identity matrix. Well, let me write this out in a little bit of detail here. I'm going to leave A as its own, but for the inverse matrix, let me call it, I know it's got n columns, so I'll just call the columns x1 through xn for now, because I'm actually going to be trying to figure those out. So multiply the A through. Then if we look at column J, so what do we have there? We have A, X sub, well, I want I because I did that last time. I better make sure that I don't mess these up. So let's put this as a very clear to see J. And using the equation that I have, this is equal to E sub J. And I gotta watch my J's. Consider the ith entry of xj. So xj is, like I said, a column of A, but let's take a look at what these could look like. So xj could look like the following. x1j, x2j, xnj. So there's my xj vector. And then, oh, you know what I should have done is, let me put it in here. xij. That's the ijth entry of A inverse. And that makes sense if you think about it. I am picking out I, and it is in, I'm picking out row I, and it's in column J already. This, remember, these x's were the columns of A inverse. So this is the jth column of A inverse. This is the ith entry in that column. Now we use Kramer's rule. So that ith item is equal to the determinant of A sub I E j divided by the determinant of A. Probably I should remind you, solving A x sub j equal to E sub j. So to solve that, this is the Kramer's rule. This is why I'm applying Kramer's rule to it. Now, for A sub I E j, we have now I need to try to figure out what this determinant is right up here. So I'm going to use this. I'm going to expand along column I. So expand the determinant of AI EJ along column I. The only non-zero entry in EJ is entry J. So the first item there will be a 0. And it really doesn't matter, but I'll put this. This is where you're going to take out the first row and the ith column, as we imagine. And then we move on, -1 to the 2 plus I times 0 times A2I plus dot plus, and then we got to finally the jth item in the list. So we're going to have -1 to the j plus I times, and what did we have there? We had a 1, and then what else did we have there? We had an a j I, like so, and then plus dot plus, I'll end it off, -1 to the n plus I times 0 times a n I. So everything's 0 except for that one thing. So we have the determinant of AI EJ will equal -1. I'm going to change these so you can recognize it more readily. Notice that the J and the I are switched from our normal convention. We have a name for this. It's called the or a cofactor. In fact, we have this formula, Cji equals -1 to the I plus j times a ji. This is the ji cofactor. So let's put some things together here. I have x sub ij from Kramer's rule. This is ei, or a sub I ej. A lot of subscripts to keep track of. Of course, this is the same as 1 over the determinant of A times Cji. So that's what x sub ij equals. C sub ji is the subscripts are reversed, so be careful with that. Remember, x sub ij was the ijth element of A inverse. So what do we get then? My inverse, I have a formula now for it. First, we'll pull out 1 over the determinant of A, and then let's go ahead and write the matrix. So we would have C11. In fact, here I'm looking at these things. The IJ and the C's flip them. The things along the main diagonal, of course, the I and the J are the same, so we don't have to worry about those. But I don't go C12, I go C21. C12 over here. So everything is opposite our conventions here. See that? So everything else, it's like basically the transpose is actually what it is. The matrix, I'll make it small, C11 up to CN1, C1N, CNN is called the adjugate of A. The notation is ADJ of A. ADJ of A equals this matrix of cofactors. All of this work has led to the following theorem. Let A be an invertible n by n matrix. Then A inverse equals 1 over the determinant of A times the adjugate of A. So, and we just did the proof right before this, so I'm not going to bother with that. Let's go right to an example. Let's use the adjugate to find an inverse. So I'm going to compute A inverse using the adjugate. And let's see what we have for A equals, I have 1, negative 2, 0, 1, 2, 1, 3, 1, 1. And let me first, before I do anything else, I need to get the determinant of A. So for that, I am going to expand along the first column here. So I'll have 1 times what matrix? Let me cancel that row and that column. And that will be 2, 1, 1, 1. And then let me take those out. I'm going down along the first column. So next I'm going to go along that row and that column. Remember, these get a negative here. So I have negative, negative 2 times what's left over. 1, 3, 1, 1. And then we'd have a plus 0 times whatever was left over. I really don't care about that part. So let me take these out. I'll use them later on. So we have 2 minus 1. 2 minus 1 is 1. Plus 2 times 1 minus 3, that's negative 2. And that equals negative 3. We'll keep that handy. So let me go ahead and start calculating my cofactors. So C11, remember the cofactor has the plus or minus sign within it, so you need to use that in these calculations. In the 1, 1 spot, I have a positive. Let me cancel my column and my row. Even though I already did it, I'll do it again. 2, 1, 1, 1. And then move across C1, 2. This one had a negative. Let me take these things out. Here I have negative 2, 1, 0, 1. C1, 3 is a positive. Here I have negative 2, 2, 0, 1. Let's move on to C2, 1. This one will have a negative. You just alternate positives and negatives. 1, 3, 1, 1. You'll notice on the diagonal, these things are always positive, because when you take negative 1 to something like I plus I, that would be negative 1 to the 2i. And when you take any negative number to an even power, you get a positive. All right, let's move on here. And 2, 2. I have 1, 3, 0, 1. The 2, 3, though, gets a negative. Whenever the sum of these indices is odd, you'll get a negative number. 1, 1, 0, 1. C3, 1 is positive. Let me take out these things. Here I get 1, 3, 2, 1. C3, 2 is negative. One, 3, negative 2, 1. And then finally, C3, 3 is positive once again. I have 1, 1, negative 2, 2. Now then, when I go to do my A inverse, that's going to equal 1 over the determinant of A. Now remember how this works. Let me give myself enough room here. The diagonals will be unchanged. We're doing really a transpose when we set these things up. What would normally be the C1, 2 position, we put a C2, 1. C1, 2 goes over there. Then a C3, 1. C1, 3. And then a C3, 2. C2, 3. And let's go ahead and put in all of those numbers. We already know what the determinant of A is. All right, let's get our numbers. C1, 1, 2 minus 1, that'll be a 1. C2, 1, that's over here now. We're going to have 1 minus 3, that's negative 2, but that negative will make it a positive 2. Move on. Where was I going here? C3, 1, this guy right here, C3, 1. 1 minus 6 is negative 5. And now let me move on to C1, 2. There's a negative in front of there. Here I get negative 2 times the negative and make that a positive 2. C2, 2. 1. C3, 2. Negative 1. Or C3, 2. Negative 1 plus 6, so that's negative 7 there. You got to watch. You have to be careful when you put these entries in. Don't do like I almost just did. All right, anyway, so C13 we have -2. C23 we have the negative out front, -1. And finally C33 we have 2 plus 2 is 4. And personally, I do not have a problem with it being left that way. I'd hate to take the -1/3 inside and then have all these fractions inside of it.